Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing basic triangle congruence theorems. More specifically, we'll be discussing 6 topics. We'll talk about the general idea of proving these basic triangle congruence theorems, and one of the first things that will come up is what's called the intermediate triangle strategy. Then we'll discuss our first triangle congruence theorem, that neutral geometry satisfies the angle-side-angle axiom. Then we'll prove the CS theorem, that is, if a triangle has 2 congruent angles, then the 2 sides opposite those angles are also congruent. Then we'll prove our second basic triangle congruence theorem, that neutral geometry satisfies the side-side-side axiom. Then we'll prove a couple of things in neutral geometry. One is a theorem about the existence of a perpendicular to a line through a point not on the line, and then we'll prove 2 particular congruences in 2 examples. This material is from section 6.2, Basic Congruence Theorems, in the book Geometry, a Metric Approach with Models by Millman Parker. The corresponding homework is this collection of exercises from section 6.2. This video is produced for Ohio University Math 3110-5110 College Geometry. Our first topic is the intermediate triangle strategy. In section 6.1, we saw the definition of triangle congruence. We started with the definition of a congruence between triangles, which means a bijection, that is, a function from the set of vertices of one triangle to the set of vertices of another triangle, such that each pair of corresponding parts is congruent. And then we defined congruent triangles to mean triangles such that there exists a congruence between them. That is to say that triangle ABC and triangle DEF are congruent means that there's one of these functions, these bijections, between the set of vertices such that corresponding parts are congruent. If the definition of congruent triangles is all you know about congruent triangles, then if you want to prove that 2 triangles are congruent, you would have to produce a bijection, that is, produce a function between their sets of vertices, and then show that all 6 pairs of corresponding parts are congruent. This is a very tedious job. Homework exercise 6.1 number 2 asks you to do this tedious job, and it's the only homework exercise of that sort. Then in section 6.1, the side-angle-side axiom was introduced. It describes desirable triangle congruence behavior. The side-angle-side axiom says this: if there's a bijection between the vertices of 2 triangles and 2 sides and the included angle of one triangle are congruent to the corresponding parts of a second triangle, then the triangles are congruent. And then a neutral geometry was defined to be a protractor geometry that satisfies that side-angle-side axiom. So now we have the definition of congruent triangles and the side-angle-side axiom being all that we know about congruent triangles. So now if we want to prove that 2 triangles are congruent, then we would have to produce a bijection between their sets of vertices and show that 2 sides and the included angle of the first triangle are congruent to the corresponding parts of the second triangle. And then finally, we'd have to use that side-angle-side axiom to show that the triangles are congruent. In section 6.2 to 6.4, we'll prove theorems that articulate other congruence conditions for neutral geometry. These theorems state that if certain other combinations of 3 corresponding parts of 2 triangles are congruent, then the triangles are congruent. A recurring strategy in proving such theorems will be to introduce an intermediate triangle. The intermediate triangle strategy is the following. If the goal is to prove that some triangle 1 is congruent to some triangle 2, then the strategy is first introduce a triangle called triangle 3, which is referred to as the intermediate triangle, and then prove that that triangle 3 is congruent to triangle 1, using either the side-angle-side axiom or later, if you know some other congruence conditions, you can use them. And then prove that triangle 3 is congruent to triangle 2 using, again, either the side angle side axiom, or if any are known, you can use some other congruence theorem. And then finally, you can conclude that triangle 1 is congruent to triangle 2. Our second topic for the video is this theorem that neutral geometry satisfies the angle-side-angle axiom. It's theorem 6.2.1. It says that if two angles and the included side of one triangle are congruent to the corresponding parts of a second triangle, then the triangles are congruent. A proof of the theorem is provided below. The proof roughly follows the book's proof, but with added statements and more drawings. You'll justify the statements in a homework exercise. Step 1. In neutral geometry, suppose there's a bijection between the vertices of two triangles such that two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle. Now notice we don't know anything at all about the remaining parts of those triangles. Statement 2 says there exists a point G on ray ED such that it creates a segment GE that is congruent to segment AB. Now again, remember, we don't know anything about the relationship between segment AB and segment DE in the original triangles. There was nothing given about that. So we have created this new point that creates a segment that we can say something about. We've created this point G, or we've said that it exists, specifically so that we could say that that red segment, EG, is congruent to that red segment, AB. Now, a remark is in order here. In terms of the intermediate triangle strategy, our triangle ABC is triangle 1, our triangle DEF is triangle 2, and this set of 3 points, EF and G, is going to give rise to a triangle GEF, and that's going to be our intermediate triangle, triangle 3. Statement 3 says that triangle GEF is congruent to triangle ABC. So in terms of the intermediate triangle strategy, this says that that intermediate triangle, triangle 3, is congruent to triangle 1. Now you'll justify this statement in a homework exercise. Statement 4 says that angle EFG is congruent to angle BCA. So this angle is congruent to this angle there. That's the inner angle. Statement 5 says that angle EFG is congruent to angle EFD. Let's zoom in on this drawing so that we can look more carefully at that. EFD is this angle, EFG is this angle. So this statement says that those angles are congruent. You'll justify that in a homework exercise. Statement 6 says that points D and G are on the same side of line EF. That is, they live in the same half plane. You'll justify that. Statement 7 is a crucial statement. It says that ray FD must be the same ray as ray FG. In other words, there's just a single ray there. It happens to have two different names. It's referred to as ray FD, but it's also referred to as ray FG. You'll justify that in homework. Statement 8 says line DF can only intersect line DE at a single point. That is, this red line can only intersect this green line at a single point. You'll justify that. Statement 9 says, therefore, points D and G must actually be the same point. Now there's a typo here. This statement 9 essentially tells us that this triangle GEF and that triangle DEF are the same triangle. In terms of the intermediate triangle strategy, that tells us that our intermediate triangle, triangle GEF, is congruent to that triangle 2, triangle DEF. Statement 10 says that triangle ABC is congruent to triangle DEF. So this green triangle, which is in terms of our intermediate triangle strategy, is triangle 1, is congruent to this blue triangle, which in terms of our intermediate triangle strategy is triangle 2. That's the end of the proof. Our third topic for the video is the CS theorem. Theorem 6.2.2 says, in neutral geometry, if two angles of a triangle are congruent, that is, if CA, then the sides opposite those angles are also congruent, that is, then CS. Here's an illustration. This picture shows a triangle with two congruent angles. This picture shows the same triangle with the sides opposite those angles also being congruent. You'll prove this theorem in your homework. A big hint is that the proof mimics the proof of the CS-CA theorem that was presented earlier in video 6.1b. The key difference is that earlier theorem, the CS-CA theorem, was proven using the side-angle-side axiom. This new theorem, the CS-CA theorem, is proven using the angle-side-angle theorem. The fourth topic is another triangle congruence theorem. It says that neutral geometry satisfies the side-side-side axiom. So if the three sides of one triangle are congruent to the corresponding sides of another triangle, then the triangles are congruent. The proof of this theorem is very long, involving many cases. The authors present a proof of one of the cases in the book on pages 132 and 133. We'll study one of the other cases, and you'll justify some of the statements in a homework exercise. Here's the proof. Statement 1 says, in a neutral geometry, suppose there's a bijection between the vertices of two triangles such that each pair of corresponding sides is congruent. Now we can label these triangles however we want. So let's label them triangle ABC and triangle DEF, with these pairs of corresponding sides being congruent. So here's a picture of triangle ABC. Here's a picture of triangle DEF. For the purposes of our intermediate triangle strategy, we should point out that triangle ABC is triangle 1 and triangle DEF is triangle 2. Step 2 says line AC creates two half-planes. We can denote one of them H subscript B. That's the half-plane that contains point B. We can denote the other one H subscript 2. That's the half-plane that doesn't contain B. Now here we've used the concept of half-planes from the plane separation axiom. Statement 3 says there exists a ray AH such that point H is in half-plane H subscript 2, such that this angle CAH is congruent to an old angle FDE. You'll justify that in your homework. Statement 4 says there exists a point B prime on ray H that creates a segment AB prime that's congruent to segment AB. You'll justify this in your homework. Now a remark is in order here. In terms of the intermediate triangle strategy, triangle AB prime C, which is not drawn yet, is the intermediate triangle, triangle 3. Step 5 says that segment AB prime is congruent to segment DE. So this segment is congruent to that segment. Statement 4 says that triangle AB prime C is congruent to triangle DEF. Now in terms of the intermediate triangle strategy, this means that triangle 3 is congruent to triangle 2. That is, our intermediate triangle, triangle 3, is congruent to one of our original triangles. Now you will have to justify this step in your homework. Now you'll have to think about that. How can you justify that two triangles are congruent? Well, we only have two tools so far that can be used to justify saying that two triangles are congruent. One is the side-angle-side axiom, and the other is the angle-side-angle theorem. Those are the only two things that you can use to say that these two triangles are congruent. So you'll have to figure out what the justification for that statement is going to be. I have provided the illustration though, and it gives you a pretty good clue. Statement 7 says that segment B prime C is congruent to segment EF, illustrated here. And statement 8 says that segment B prime C is congruent to segment BC, illustrated here. Statement 9 says that line AC must intersect segment B prime at a point G that's between B and B prime. Here's an illustration. You'll justify this in your homework. Now notice that I've drawn G between A and C, but we don't actually know that that's where G is. In fact, there are 5 possibilities for the betweenness relationships among A, C, and G on that line AC. The 5 possibilities are shown in these drawings. It could be that A is between G and C. It could be that point G and point A are actually the same point. It could be that G is between A and C. And it could be that points G and C are actually the same point. And it could be that C is between A and G. Those are the 5 possibilities. So we have a big OR statement here. We have a statement that says either this is true, or this is true, or this is true, or this is true, or this is true. Well, remember that in a proof, when you arrive at an OR statement, you are set up to do a proof by cases. So that's what we do from here on. We have a proof involving 5 cases. Now remember what the goal of the whole proof is. The goal is to prove that triangle ABC is congruent to triangle DEF. Well, now we have to prove that that is true in all 5 cases. Well, in the book on pages 132 to 133, the authors present a proof that this congruence is true in case 1. And they point out that the proof for case 5 would be similar to the proof that they give. So we can say that therefore that congruence, triangle ABC congruent to triangle DEF, is also true for case 5. Now, as the authors point out, and I'll agree, in cases 2 and 4, that's this case and this case, in those 2 cases, it's fairly straightforward to prove that triangle ABC is congruent to triangle DEF. So I won't discuss those. In this video, I'll be proving case 3. So we will suppose that we're in case 3. We'll suppose that G is between A and C, as illustrated here. And we'll go from here. And our goal, again, is to prove that this triangle congruence is true in case 3. So far we've supposed that G is between A and C. So we have this configuration of points. Statement 15 says that angle ABB prime is congruent to angle AB prime B. So these 2 angles marked in green are congruent. You'll justify that in homework. Statement 16 says that angle CBB prime is congruent to angle CB prime B. These 2 angles marked in black. Now we need to establish that point G is in the interiors of 2 angles. Statement 17 says that point G is in the interior of angle ABC. That's shown here. Statement 18 says that point G is in the interior of angle AB prime C. That's illustrated here. You'll justify those statements. Statement 19 says that angle ABC is congruent to angle AB prime C. So these angles that are marked in red are congruent. You'll justify that those are congruent in your homework. Statement 20 says that triangle ABC is congruent to triangle AB prime C. So this triangle here is congruent to this triangle here. Now in terms of the intermediate triangle strategy, we've proven now that triangle 3 is congruent to triangle 1. Statement 21 says that triangle ABC is congruent to triangle DEF. And that's illustrated here. This triangle is congruent to this triangle. In terms of our intermediate triangle strategy, we've proven that triangle 1 is congruent to triangle 2. That was the goal. Now we've just proven that it's true, this congruence, in this case, in case 3. We need to wrap up the cases though. We need to write a conclusion of cases. That is, we need to write this, that triangle ABC is congruent to triangle DEF, just without reservation, because it's true in every case. So we proved that it's true in case 3. Those other cases were discussed earlier. So since this congruence is true in every case, we just say simply that the congruence is true. Now, I have a remark written here that's actually wrong. I'm going to just cross this out. The fifth topic is the existence of a perpendicular to a line through a point not on the line. So recall an earlier theorem, 5.3.5. It said that in a protractor geometry, if B is a point on line L, then there exists exactly one line L prime such that L prime contains point B and L prime is perpendicular to L. Now notice that that theorem is a theorem of a protractor geometry. That's true for any protractor geometry. There's a related theorem in neutral geometry with point B not on line L. That's this, theorem 6.2.5. Now here there's a typo. This should say in a neutral geometry. In a neutral geometry, if B is a point not on line L, then there exists at least one line L prime such that L prime contains B and L prime is perpendicular to L. There's a proof of this theorem in the book. It's very similar in style to the proof of theorem 6.2.3 that was just presented. So for that reason, I won't discuss the proof of this theorem in the video. Now, it's worth saying again that this is a theorem of neutral geometry. You'll see that if you look at the book's proof, somewhere in that book's proof, they use a fact that's true in neutral geometry. They use the side-angle-side axiom, or maybe the angle-side-angle theorem, or maybe they use the side-side-side theorem, but they use something that requires that we know that we're in neutral geometry. Our sixth and final topic is proving some particular congruences. We'll do two examples that are similar to some of your homework exercises. The first one is similar to 6.2 problems 5 and 6. It says this: prove that in a neutral geometry, if triangle ABC and points D and E satisfy this betweenness relationship and this angle congruence and this angle congruence, then they satisfy this segment congruence. So those are all illustrated here. You can see that here's a drawing of the hypothesis. We can see that the points satisfy that betweenness relationship. They satisfy that green angle congruence, and they satisfy that blue angle congruence. And here's an illustration of the conclusion showing that those points satisfy that segment congruence. Well, here's the proof. Suppose that all that given stuff is true and the hypothesis is satisfied, so suppose we have that configuration of points. Then we can say that segment AB is congruent to segment AC by statement 1 and the CA arrow CS theorem. So there we've used one of our new theorems. These two segments are congruent because they're opposite these two angles that are congruent. Notice the illustration that I have drawn. I've drawn a single triangle containing those congruent angles and those congruent sides. That's important because this theorem, the CA arrow CS theorem, can only be applied to a single triangle. You have to be able to identify the triangle that you're using when you invoke that theorem. Statement 3 says triangle ABD is congruent to triangle ACE. You can see them shaded in that drawing. Notice that we've used theorem 6.2.1, angle side angle. This might be the first time that we've proven triangles are congruent not using side angle side. Statement 4 says, therefore, these two segments are congruent by the definition of triangle congruence. They're congruent because they're part of, they're corresponding parts of two triangles that are known to be congruent. That's the end of that example. Let's go on. Example 2 is similar to problem 6.2, number 8. It says, prove the following. In a neutral geometry, if a triangle ABC and points D and E satisfy these betweenness relationships and this green segment congruence and this blue angle congruence, then they'll satisfy this red segment congruence. Here you see a drawing of the hypothesis. The points satisfy those betweenness relationships, and they satisfy this green segment congruence. Now it's tricky to illustrate this kind of thing in this drawing because segment AB goes right through point D. So that's why I've used color in my illustration. And there you can see also that the points satisfy that blue angle congruence condition. And then here's a drawing of the conclusion showing that the points satisfy this red segment congruence. Well, here's the proof. We start by saying all the given stuff and the hypothesis in a single statement. Suppose that in a neutral geometry all that stuff is true. Again, the hypothesis goes all in statement 1. And here's the illustration of the hypothesis. Statement 2 says that segment BC is congruent to segment CB. Now that's because a segment is always congruent to itself because it has the same length as itself. Here's the illustration. Statement 3 says angle ABC is congruent to angle ACB using the CS CA theorem. So here again you see an illustration where I show clearly the triangle that has those parts in it and that I'm using that theorem on. And I don't show other stuff that's not part of that triangle or part of what's involved in this statement. Statement 4 says triangle BCD is congruent to triangle CBE. Now notice that these triangles were overlapping in the original drawing. Those triangles are in there. It's confusing to talk about them though when they're overlapping. So here I've just simply pulled them apart. I'm saying that they're congruent, and when they're pulled apart like this, you can see very clearly why they're congruent. They're congruent by angle side angle. Notice that if these triangles were left in the original drawing, it would be very hard to understand this because this angle would be cluttered up with this angle, and it would make this statement very hard to understand. The final statement of the proof says that therefore these two segments are congruent, and that's by the definition of triangle congruence. These segments are corresponding parts of triangles that have been proven to be congruent, so therefore these segments are congruent. Well, that's the end of that proof of that example, and that's the end of the video. Thank you.